Welcome, everyone. I'm Moshe Tanach, co-founder and CEO of NeuReality. That's how my title goes, but I'm more of a system and semiconductor engineer based on my 27 years of experience. And I'm here today to talk to you about AI deployment, inference. Where's the clicker? This one? And how we need to liberate the world data center to allow ubiquity and mass deployment of AI use case. And I'll start by looking at the amazing. So I wanted to start to look at the amazing decade that just passed by, and the last 2 years with the amazing innovation we're seeing on the infrastructure level. A few weeks ago, here in San Jose, in GTC, Jensen announced 120 kilowatt worth of rack with 36 CPUs, 72 GPUs, miles of connectivity inside the server. And we're seeing hyperscale, supercomputing infrastructure being deployed and allowing us to develop amazing capabilities. Just in the last year, we saw multimodality coming into play, mixture of experts, huge LLMs, small LLMs with agents, and above that, new type of use case to create video. This is very sensitive. To create video, we even have prompt engineering, a new type of engineering type to use AI better. But I want to spend the next 20 minutes without diminishing the progress we've made on how we transition from developing AI capabilities to deploying them in mass production in every aspect of our lives. And I'll start with a bet. When you look on this view and you see these 4 sport cars, what's your bet? Who's gonna reach the first mountain stop first? So I guess you want to see the spec of the cars, the size of the engine, the traction system, the gear, and who's the driver. Now, what if I ask the question again on this slide? Now, who's gonna be first? What I'm trying to suggest is that just pushing the strongest processor, the strongest AI accelerator is not enough anymore. And we've seen the NVIDIA H100 and the B100 that are coming. We've seen TPU V5, wafer scale technology from Cerebras, but faster AI accelerator are just not enough anymore. And I want to spend the next 20 minutes to kind of look at inference and AI deployment from multiple angles and what we need to do as an industry in the next 5 years in order to make it ubiquitous. So what defines the success of technology? Usually success is defined by ubiquity. And if you look on the continuum of AI, since 1943, when the first neural network was used to imitate the behavior of a person, and the Alan Turing test in 1950, until today, where we're using supercomputers to do amazing generative AI, large language models, multimodality, and all this, I'm suggesting that we've hit a wall. And actually, by the end of the year, Gartner are reporting that 50% of the companies that are developing, researching LLM will drop it because they don't see enough value for the investment that they invest. And this can change, and we have to change. I'm saying there's an urgent focus that us as an industry need to focus on inference. And some of us have been doing it. If you take the Inferencia card in Amazon, if you take the Qualcomm AI 100 card, that is very good inference acceleration system compared to anything out there. But there's many other angles that we need to tackle in order to make AI more deployed. Let's look at where we are today. Just based on the last couple of weeks, the cost of deployment is skyrocketing. 90% of business would be pumping their brakes on AI development. That's what some articles are saying. In terms of energy consumption, there's a real problem. In California, there's no more power capacity. Virginia, North Carolina are building more data centers than they have today. And we're going to hit some limitations on power delivery. And last, there's only 35% of reported adoption for AI globally. And you'll be surprised, in the US, it's only 25%. China, by the way, is above 50%. And most of it is not really mass deployment. It's more training, research, development of capabilities. So if we want to see a path to affordable intelligence, we need to think about cost. We need to think about the energy consumption, about the user experience, and this is an important piece, and about real estate. You know, many data centers today in the US, for financial services, for instance, have empty racks. A rack with power supply of 13 kilowatt can bear only one DGX H100. Of course, they can't buy the new Blackwell rack of 120 kilowatt. So actually, they're running out of real estate because they have empty racks across the data center, and they're looking for more real estate space in New Jersey or where the headquarters is. So let's look on multiple angles. The first angle I want to talk about is differences between data centers. This is a meta facility, but when you look on the difference between hyperscalers and enterprise, for hyperscalers, data center is their business. But for enterprise, this is just a business expense. Their business is something else. Hyperscalers will build millions of square foot, while enterprise will build thousands, sometimes only mini data centers, hundreds in regional retail shops and places like this. Hyperscalers can take their data center and power plant, own it, build it in a rural area. For many enterprise, they need to build it in their headquarters or close to the biggest campus. And it goes on and on in terms of when you build a million square foot with tens of thousands of servers, you can optimize your IT infrastructure. You can go to PUE, power utility efficiency of 108 that one of the hyperscalers had reached recently. But for enterprise, it stays in 158. PUE is the 108 means that we're spending 8% of power that is not feeding the actual equipment that we bought. For enterprise, it's 58% in average. But the cost of improving it cost more, the investment cost more than the value of it, so they don't do it. And it goes on and on. It's a very different method to build a hyperscaler data center versus an enterprise. The other comparison I want to make is training versus inference. In training, this is your R&D capabilities. You're building them, you're spending it from your R&D budget. You're using supercomputers, gigantic data sets. You split between hundreds and thousands of GPUs in order to train faster. You're using high precision, high memory bandwidth. So you'll probably try to find the highest memory bandwidth you can get, HBMs and stuff. And all this is making the process very expensive, very performant, but it leaves out of your R&D budget. When you're looking on inference, this is when you deploy your trained model. This is where you care about the cost of sale, you care about your margins. And in many markets, like take smart city, there's no money in smart city because the city of New York, the city of San Francisco don't have enough budget to consume all the video streams across the city and bring value to theft prevention or traffic management and stuff like that. So how do we change that? We need to understand that one equipment, one type of AI infrastructure can't feed all. Like Google 4 years ago, they were saying, we're taking an avenue that TPU cluster will serve everything. Well, it's not the case anymore. You have to drop down the cost, the power consumption, the real estate effort, overhead, in order to make inference efficient enough for all those industries to deploy it. The last one I want to take a look on is large language model versus small language model. All of them are large, but now when we're talking about large language models beyond trillion params, Mistral looks like a small model, although it has 7 billion. So with large language models, we're talking about above 100 billion parameters, GPT 3.5, 3.5, 4, Claude 3, Bloom, DBRX from Databricks. We need the front-end network to connect the storage and the clients to the training system, but we also need the backend network to connect all the GPUs together. We need to provide large scale of computing and storage services to keep those engines busy while they train the model. I mentioned it before, we need very high memory bandwidth because currently the schemes we're using are limited by the memory bandwidth that we give our processing elements. In small language models, we can fit into a single chip or a single node between 2, 3, 4 chips. It's less complex in terms of serving a high data set and data commute. You need to focus on connecting a lot of clients to a lot of servers for quality of service. So you focus more on the front-end network. And in order to provide something very efficient, it's better not to use a backend network at all. If the GPUs need to communicate between themselves, let them do it inside the node over PCI. And there's a lot of investment that need to be done on the data science and algorithm side. We can make LLMs much more efficient, much faster, and much less costly. And I brought here a lot of techniques that are in development today, and I'm sure we're going to see more. I always say that an engineer, if you define the problem and you insist that it has to be fixed, an engineer will solve it. And we can take Mistral, Mixtral, multimodality, RAG systems and make them very, very efficient, 50x times more efficient. If we'll just start using additional transformations, compression of the data that we communicate with our memory or communicate between GPUs or between the client and the server. It's just that in the past 10 years, most of us were focusing on solving bigger and bigger problems, bringing more and more capabilities. And now is the time to shift focus and think about how do we make them efficient enough to be deployed everywhere. What if we do nothing and we keep going? Then who will be able to afford it? Of course, the hyperscalers, big manufacturing companies that have a lot of investment in every facility. Take TSMC, for instance. It takes billions of dollars to build a new fab. Life science companies that invest a lot in R&D research. But who will be left behind? And here, we're losing the retail and food beverage. You know, Amazon had these automatic checkout stores, but they're pull out the plug. They're not growing it anymore because it's not economically viable yet. Public transportation, public safety, all those things that can really enhance the quality of our life and our growth as a society will not be able to be pushed forward unless we wait 10 years for another 5 process nodes to advance in TSMC and Samsung and Intel. So I was trained in the Army to lead by example. So I'll take you through what we do in NeuReality very shortly. My marketing VP insisted that I'll do some marketing as well. And I'll show you what we're doing together with some of our partners, Qualcomm included. That's how every inference server is built today. It's practically a CPU-centric architecture. And the AI Accelerator, which we called Deep Learning Accelerator, a DLA, are hanging off a PCI connectivity. Sometimes it will have a backend network that connects all the DLAs, sometimes it won't. The most efficient one is not to use the more expensive. You take the L40S from NVIDIA or the AI100 from Qualcomm or other AI accelerators that are very efficient for inference, and you connect them to the CPU. Now, this is a backend server that is waiting for model provisioning requests and queries coming from multiple clients inside the data center, out of the data center. And what happens is that all this pipeline above, network termination, queuing and scheduling between all the clients, pre-processing of the data to prepare it for the GPU are just making the CPU congested. So we paid a lot of money on an expensive x86 or ARM core, and you can see what NVIDIA are doing right now, right? It used to be 1-to-4 ratio or 1-to-5. Some chassis will have 10 cards inside and 2 sockets of CPU. But now the new Blackwell rack design is doing 1-to-2. So you have to pay for an ARM server, ARM CPU, for every 2 GPUs. And practically, as an industry, what we're doing, we're throwing hardware on the problem instead of solving it from the architecture level. So what we have done, we define a new type of a device that is called Network Addressable Processing Unit. This is the NR1, and this is a linear scalability architecture. The more GPUs you put, the more front-end chips from us you put. And now you open the bottleneck, and it's not that we just packed the CPU and the NIC in a device. It's actually a heterogeneous compute device with video decoders, audio codecs, DSP engines, and ARM cores as the last resort. And there's a hypervision layer that handle all the queue management, the stage pipeline, and the sequencing in hardware instead of software. So now when you offload it to hardware, you don't need to live in one cache subsystem, memory subsystem with a lot of contention between the different CPU cores. When you look inside the chip, you'll see a very small and efficient network engine with a network protocol that we invented that is called AI over Fabric. If any of you is familiar with the storage industry, with NVMe over Fabric, it's a protocol layer sitting on top of TCP, Ethernet, or Rocky V2, and providing much higher efficiency on commuting data between the clients, sending the batch of images or tokens in a more efficient way. And last, we have the AI hypervisor that handling the queue management, scheduling, dispatching, and all the programming. If any of you worked with NVIDIA cards or others, you know that the driver that runs on the CPU, that manage the accelerator, is consuming a lot of CPU power. So instead of running those drivers on our ARM cores, we're offloading them to run inside the AI hypervisor. This is the JPU, Job Processing Unit. These are small RISC that we train to understand how to program any card, and then they do it in hardware instead of on the big CPU. So just for comparison, when you're looking on LLMs, when you're building NR1S, a full system with 10 NR1 cards and 10 AI100 from Qualcomm, let's say, you can get half the price. It's $200K versus $400K compared to the DGX H100. 6.5 times more data processing when you consider offloading the data paths, the pre-processing, the queue management, quality of service, and networking that we have in NR1. And it's half the real estate, 4 rack unit instead of 8, and third, the power consumption. And now you can, for an example, when you run Mistral, you can get to 304 tokens per $1,000 compared to 74 when you run with DGX H100. So you see, just by insisting on bringing a different system architecture, and this is only one angle, we can drive efficiency 4x, reduce 75% of the cost and the power consumption that we're consuming, investing on our AI usage. These are the kind of things that I wanted to inspire you today to do more. And whether projects within your companies or new startup ideas to handle. That's the 3 AI accelerators that we support today: AMD V70, Qualcomm AI 100, and internally in IBM with their AIU accelerator. But we can plug in here the L40S or any type of AI accelerator that come in a PCI chem card form factor. So to conclude, exploring and developing capabilities need to be shifted, are driven by supercomputers today. And it will continue to be this way. And the hyperscalers will continue to do liquid cooling and improve their power plants. And this will drive capabilities. Leveraging these new capabilities is dependent on us as an industry, putting more effort into making them ubiquitous and deployed everywhere in much more market segments. And the opportunity is huge. There's a blue ocean of opportunities to use more AI. All the buzz that we're hearing is still 80% research and development of capabilities. We need to flip that if we want to take it to the next level. Or maybe we don't. Maybe we're afraid of it. I don't know. We need to bridge the gap between capabilities and economic viability. And it's a multi-angle challenge. And gladly, it involves a lot of innovation on multiple fronts. Fixing the source of the problem is something that NeuReality does, just generating new architecture and compute infrastructure that consume less current. But there are other angles like investing in better cooling and power delivery infrastructure, innovation on data science and algorithms that will improve how we run LLM and how efficient they are. And last, disaggregation, virtualization, and composability in data center. This is a piece that I can give a whole lecture on. Still, a lot of customers load their application and their AI acceleration on the same instance, and it's the wrong thing to do. When you do that, you can never perfectly balance the amount of general purpose compute you need and AI acceleration. Look at storage. No one is thinking to do direct attached storage anymore. We're all using NAS or Sun technologies, S3 in Amazon or NetApp, Dell EMC. That's the transformation we need to do for every function in the data center. And NeuReality just do it for AI inference. So we're building an AI inference appliance that is practically the same as the storage appliance that you buy today. You don't need to muck with developing it, developing the server application. You can just buy it as is, and it has APIs to provision models and to send queries from any clients to consume those models that you provision. Of course, the tool chain that allows you to compile your pipeline. So going back to the race, it's much more complex, and that's the world we need to build. You know, some cars will have wings, more highways, and then when you look at the problem from all angles, you solve it differently. The future is dependent on a multi-angled solution. We just announced our developers portal. You can swing by our booth and meet the team and see if we can help you with inference, or if you can help us, make the next leap in AI in the AI market. Thank you very much. And if I inspired any of you to go and work on deployment and leave the rest to work on more capabilities, then I did my thing today.